How does this incredible skyscraper defy the laws of physics and stay standing?
This house always is on the verge of falling down.
What happens when one of the world's richest men and its most extreme architect create the impossible?
But obviously we know that levitation of buildings hasn't been invented yet.
And how do you build a 300-meter-high elevator in an area so remote, heavy machinery can't be used? This is the age of the extraordinary.
Where else can you swim from one skyscraper to the other 300 feet in the air?
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now, their secrets revealed. Discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? New York's Manhattan Island, where the skyscraper rules the roost. Ever since the first one went up over a century ago, the drive has been to push towers taller and cheaper. But the resulting demands on engineers have created repetitive, predictable shapes. Creative flair and groundbreaking design were rare exceptions. That was until 2017, when in Manhattan's Tribeca district, a spectacular new tower was unveiled. This is 56 Leonard Street, where a team of engineers and architects stepped over the cutting edge, ripping up the skyscraper rulebook.
The shapes are extraordinary. I mean, boxes stacked on one another, and some of them are slid out. The whole thing looks so precarious.
At Leonard Street, 56 stories of unique apartments are stacked ever more daringly right up to its 250-meter summit. Here at the top, engineering logic seems to have been recalibrated to defy the laws of gravity.
It all just looks a bit scary.
Unique apartments with sky-high, impossible overhangs created a complex and expensive construction. So how did they build it? Even more than most cities, Manhattan is space-hungry, resulting in tall buildings with simple layouts that are a compromise between the engineering challenge of building a skyscraper and the practical economics of doing it at a price.
Most skyscrapers or tall buildings are either rectangular or tubular because those are really efficient shapes when it comes to supporting themselves.
For construction purposes, and developers like to have buildings be fairly regular, columns going straight up, etc., so that every floor is the same and they can just build it nice and quickly.
These uniform layouts are now so efficient to build that a conventional high-rise with over 50 floors can be completed in just weeks. But the results are often a little underwhelming.
Imagine you wanted to change things up a bit.
You could put this cantilever section in there, this box section in there, and you might even want to, like, take out bits. Whoops.
Changing it up in the world of skyscraper construction means taking risks. But that wasn't going to stop developer Isaac Senbahar.
We knew this was going to be a very tall structure and very visible from almost every angle in the city. So we said, okay, we have a responsibility to do something iconic. We didn't want something repetitive, some just straight up building. We wanted something more interesting, more sculptured.
When Isaac bought the site in 2008, Tribeca was not one of Manhattan's glamorous residential districts. But building something special anywhere in New York is expensive. So these apartments would have to command top dollar. Needing a design that would attract the uber-rich, Isaac headed to Europe and world-renowned Swiss architects Herzog and de Meuron.
We felt that Isaac was ready for a new approach, a more radical approach.
Herzog and de Meuron's portfolio includes some truly incredible buildings, like Bayern Munich's Arena Stadium and London's Tate Modern Extension. But no skyscrapers.
Even if we had done a building before, a tall building, we would always look at it from a different angle and would give him something unexpected. We wanted to be a stack of apartments, but not an anonymous one. The building could be understood as a pile of individual pieces, even in the middle part, and then the top, which would have even more exclusive apartments, which we decided could become like stacked private homes. And I think that's really new and hadn't been done before anywhere.
There's good reason it's never been done before. In order to make a strong, stable, tall building, irregular spaces are normally built into the super-stable lower floors, with smaller structures at the top. The architect's concept that the higher the apartments are, the more off-balance they appear, flipped conventional high-rise engineering on its head. To pull this trick off at the top, they needed to reduce structural complexity lower down, while still making the floors appear to be different. To do this, they hatched a cunning plan. The first 46 floors would be built in the conventional way, using continuous outer columns and inner walls to provide support for the floors above. The floor layouts would also repeat, but they'd been made to appear different by changing the size and position of balconies and edges. The 46th floor would be unoccupied, and so could be packed with load-bearing walls, creating a 47th floor plate that would be a super strong, super stable platform for the rest of the floors above. Skyscraper specialist Hez Zimena was the engineer tasked with making it happen.
We tried to stiffen up the building enough up to the 46th floor, so when we reach the 47th floor, the first Sky Villa, the building will have sufficient stiffness that we can have the flexibility of doing whatever we want structurally and give the architect the freedom to do whatever he wants with the space.
And what the architects wanted was to create an extraordinary visual effect.
If you make this upper box, let's say, hover to a certain degree, you don't make it hover so it collapses. You can push it to an extreme, you know, like in Chaplin's movie, you know, where this house always is on the verge of falling down. Together with the structural engineer, you find the right moment between something fragile, something even dangerous.
That vision for off-balance apartments that still had wraparound views meant pushing structural concrete engineering right to the edge. The lower floors used conventional skyscraper engineering, where continuous columns share the load. But because the top 9 floors were all offset, that same system wouldn't work. Each of these floors had to be stiff enough to support huge cantilevered overhangs, some over 7 meters. And they had to do that without compromising the view from within. To pull it off, engineers turned to a 125-year-old idea: the Vierendeel truss. A regular truss uses diagonal cross members to create triangles that make it very strong both laterally and vertically. But the views from within would be ruined. A Vierendeel truss connects the two floors using only vertical columns, so it's just as strong vertically, and it keeps its lateral strength through the massively strong central lift shaft column that also connects the floors. So the Vierendeel truss allows huge openings, and the apartments above can be offset with crazy overhangs.
A Vierendeel truss is actually a brilliant solution for a long cantilever. They were developed by Alton Vierendeel, a 19th century Belgian engineer who developed the super strong truss, particularly resistant to bending forces.
The advantage of utilizing a Vierendeel truss is that it's not obstructive architecturally. Like traditional truss would have a diagonal member crossing through the space, and that would be very obstructive architecturally, and it's kind of prohibitive. So we came with a different approach.
So this is how the Vierendeel truss became the key to building the sky villas. On super stable floor 47, concrete columns are precisely placed where they will give support to the floor above. This creates the first Vierendeel truss. The central lift shaft provides all the lateral strength, so the floor remains beautifully open plan, but can still support the tremendous downwards forces from the 8 unique stories built on top. These trusses create such rigidity that the upper floors don't have to sit directly on top of one another, allowing the amazing overhangs. All helping to make the sky villas some of the most spectacular homes in the world.
There's literally nothing underneath us other than the slab, and then it's straight down to the street level, 800 feet below us.
Not only are they over 200 meters up, but at up to 550 square meters, the 9 sky villas are huge, each exclusively occupying its own floor and each with a unique layout. Situated in up-and-coming Midtown Manhattan, it was hoped homes here would fetch sky-high prices.
This is a building aimed at some of the wealthiest people in New York.
The lower apartments up to the 45th floor would be priced between $3 million and $10 million, while the plan was the sky villas would sell for over $20 million. And those hefty price tags were needed, as it became clear the top 9 floors, with their unique layouts, were going to be slow and expensive to build.
You know, you do 3-4 floors of all the same thing, and then you're used to it, then it's just automatic.
But of course, Herzog's 9 sky villas were all unique.
Every floor plate is a different size and shape.
So every floor was kind of, there was a learning curve. And then you learn that, and now it's a new plan. It's just like, you know, the game changed every time we poured.
Because each of the sky villas is different, before work could start on the apartment above, the one below needed to be strong enough to support it. And that meant more time for the concrete to set.
The biggest challenge for the contractor is to hold the forms and the scaffoldings in place until the concrete cures and reach its required strength, and then he can remove the scaffolding and the temporary supports.
You know, in New York, we used to pour 1 floor every other day. Here, some floors took 6 weeks.
By 2014, the lower 46 floors had taken 20 months to complete. And with the top 9 floors set to take 9 more months, extra measures were taken to make the site safe and weatherproof.
It was actually very interesting to see during construction that it had this black curtain protection around the entire 10 floors. Once everything cured, they start stripping down the scaffolding, and then this beautiful structure, it's almost like a sculpture, revealed itself to the public.
So, with patience and engineering ingenuity, the impossible overhanging sky villas had been created. But before anyone moved in, the building needed protection from something that spells trouble for any skyscraper: the wind.
Tall buildings will always move in the wind, and that can't ever be completely stopped, and they'll always move, in some cases, by quite a lot.
New York has recorded winds of up to 100 miles per hour, and Leonard Street's sheer height and comparative isolation from other scrapers means in high winds, it can move by up to a foot at the top. It's engineered to handle this amount of flexing, but left unchecked, these movements can keep on increasing, potentially collapsing the building. So it's crucial there's something to counteract these forces.
A lot of skyscrapers have what's called mass dampers. They're basically counterweights. So for example, if the wind is pushing one way, the counterweight pushes the other way.
Most skyscraper counterweights are large suspended blocks like this. But at Leonard Street, they chose a damper system sometimes used to cope with the ultimate threat to buildings: earthquakes. Skyscrapers in earthquake zones have water tanks to cope with the swaying induced by a massive quake. This is what 56 Leonard Street uses.
At the top is a giant tank of water. When the building moves one way, due to the wind, the water in the tank moves in the opposite direction.
So 56 Leonard Street was ready for the forces of nature. But in 2016, just a year from opening, the engineers needed to get the inside prepared for new residents. To do this, a twist was given to an otherwise ordinary feature: the lobby staircase.
You have a stair, so do the stair in a way that it's nice to walk up and down. It's inviting, I would say, to take the stair, if it's 1, 2, 3 floors perhaps.
As usual at 56 Leonard, the stairs would be made of poured concrete.
So the way to design something in concrete, it's called formwork, and it's really simple. It's basically just creating a mold of whatever shape you want and pouring the concrete in, letting it dry, and there you have it.
Sounds simple. Except when the pour involves nearly 50 tons of concrete, and the architect is demanding a seamless finish for his stairs. A seamless finish is created by not letting the concrete set between pours, so preparations needed to be meticulous.
5 months to plan the stairs and create the mold that the concrete would be poured into.
It started with experts conducting the whole pouring because concrete has air bubbles in it, and that's why they use vibrators. This guy was conducting everybody where to use the vibrator. It was a very, very precise operation and a long day.
The carefully poured staircase was typical of the attention lavished on every inch of this building. Once finished in 2017, the quality of Leonard Street was obvious. But potential buyers had understood this was a special building way before that. Sales had opened in 2013, and almost immediately someone agreed to pay $47 million for a sky villa. A record for any address below Midtown Manhattan, and a sign that the risks taken by its developer would pay off.
I think we broke a record. We sold close to $1 billion in 9 months.
2.5 million man-hours, 27,000 cubic meters of concrete, and 5,000 tons of steel went into creating Leonard Street's 46,000 square meters of space. It had taken over 5 years, but a towering landmark now graced Manhattan's skyline. And if proof of its success was needed, locals have affectionately given 56 a nickname.
Someone spoke of the Jenga tower. At the beginning, I didn't even know what he was talking about. But people like it, and if people like it over a certain time, this is a good sign.
It was difficult, it was 10 years of my life, but to build a building like that in the skyline, it always feels good that, you know, you've built something like that.
56 Leonard is remarkable. I mean, it stretches the limit of what's possible to build, what's structurally possible, and then celebrates that.
"12,000 miles from the man-made towers of Manhattan are Mother Nature's skyscrapers. The towering sandstone columns and miniature rainforests of Zhongjiajie National Park in central China are a unique spectacle on planet Earth.
This is a UNESCO World Heritage Site. Beautiful, yet strange landscape. There's nowhere else like it.
Unsurprisingly, millions of people want to see it. And what's the best way to enjoy that incredible view? By taking the world's tallest outdoor elevator. The 326-meter-high elevator of 100 dragons is better known as the Bailong elevator.
This is the elevator that hangs off the side of a cliff. It's taller than the Eiffel Tower, taller than the Shard in London.
The site was so remote that heavy machines couldn't be used to build it. All the work was done by hand.
It carries 1,380 passengers an hour, and all in the middle of an earthquake zone.
But laser systems and escape tunnels keep the tourists safe from seismic danger.
And if you don't want to take the elevator, you can just go ahead and take the 999 stone steps.
Stepping all over the park is exactly what thousands of people used to do. In the 1990s, word about the stunning landscape spread, and soon huge numbers of curious tourists were tramping through the delicate forests and climbing its fragile rocks. Its ecosystem was suffering. The Chinese government had to act. One of the best views of the park is from this peak. So to keep visitors under control, but still let them see the incredible natural wonder, they built this astonishing elevator. Half inside, half outside, a huge rock face. The visible upper 172 meters is actually only just over half the elevator's total height. The lower 154 meters is hidden in shafts tunneled inside the cliff, and at the bottom of those is a 200-meter access tunnel leading to the main concourse. It all works smoothly now, but its creation was an epic feat of human endeavor and engineering. The first stage was to tunnel into the mountain to where they were going to build the base of the lift shafts. Today, it's used by hordes of visitors to reach the elevators after they've got off their coaches. But when the project was started in 1999, road access was severely limited, and no heavy equipment could be brought in. Liu Qie is manager of the elevator facility.
We used 100% human labor, with no heavy equipment and industrial machines used during construction. Workers carried all the equipment and materials on their shoulders or with their hands to the hillside.
So using only hand tools, the tunnelers got to work.
We first dug a tunnel into the mountain at its foot. Then we drilled the elevator shaft in reverse, from bottom to top.
Yes, you heard correctly. They drilled the shaft upwards. This is called reverse circulation drilling.
Drilling wells from bottom to top is actually very difficult and dangerous, as the wells above the workers can collapse at any time, and yet workers had to keep drilling upward.
With the 154-meter shaft reinforced, the exposed mountainside above needed to be made much more stable and strong before it could take the weight of the elevators.
More than 4,000 rock bolts were inserted up all 326 meters of the mountainside, and anchor cables were connected to the rock bolts so they could surround the mountain.
With the huge column of rock tightly wrapped with steel cables, wire mesh was added and concrete sprayed over the top to create a rock-solid mountainside. Next, the huge steel derricks, or frames, were bolted onto the reinforced cliff face. Finally, the elevator cabs could be installed. Those 3 huge double-decker cabs can each carry a payload of almost 5 tons, or over 50 people. With their high speed of over 5 meters per second and world record 326-meter climb height, they demand state-of-the-art control systems. Computers keep the cabs balanced and smooth in transit. To save power, electrical energy is recovered by the motors as the cabs descend. But perhaps the most important engineering at Bailong are the safety systems. Because the stunning beauty of the Zhongjiajie region hides a deadly threat.
It is an earthquake zone where they've had historically quite significant earthquakes that have killed a large number of people in the vicinity and in the surroundings, and it's something that could happen again.
With the elevators in almost constant use, raising over 20,000 people up to the viewing platform every day of the week, the consequences of a major quake could be catastrophic. So Bailong's engineers have built in every safety feature they could to quake-proof the structure.
We have 7 wire ropes above the cab, and actually every single one of them can hold the weight of the cab. The second safety measure are the guide rails along both sides of the cab. The cab is tightly fitted to these rails and has brakes which will stop the elevator from falling, even if all 7 cables fail. The third safety guard are the 4 hydraulic bumper posts we installed in the elevator pit. This is to soften the impact of the cab if the other safety gear fails to work.
Of course, prior warning of an earthquake would be the best safety feature of them all. Just a few seconds warning could save hundreds of lives here. So a system of lasers is sited on distant hillsides, which train back to receptors mounted onto the steel structure.
The lasers shining across the mountain are extremely sensitive. They can monitor the tiniest of movements in the earth and can notify the control room to perform evacuation procedures.
Just a few millimeters of movement will trigger the alarm, and instantly the elevators will automatically take passengers to one of the evacuation exits, built every 11 meters into the cliff face. But for now, the Earth moves only for those lucky enough to gaze at one of the planet's great natural wonders.
Since 2015, we have experienced an explosive increase in the number of visitors, with about 4.5 million tourists coming here in 2018.
The park is now the second most popular tourist attraction in China, and it's being kept in pristine condition. All thanks to the engineers who figured out how to build this incredible elevator. Paris, France. Carefully planned, very traditional. Famous for its immaculate boulevards and ornate apartment buildings, all combining to create its unique character. No wonder when bold new structures are proposed, it often takes a while before the Parisians appreciate them. In 1889, the Eiffel Tower was described as a truly tragic street lamp. In 1977, the Pompidou Center simply monstrous. And in 2006, a new building joined their ranks.
This building is definitely out there. It's weird. You look at it and you're like, is it a broken perfume bottle? Is it a giant ship? Is it a UFO from outer space?
A building designed by one of the world's greatest architects that locals hated and set out to stop.
In Paris, it's difficult to imagine this kind of building.
Bankrolled by a billionaire, money was not the problem. Figuring out how to build it was.
I think it's fair to say there were some very dark days in the process of putting this building together.
The challenge of creating this astonishing building took hundreds of engineers, architects, and craftsmen, 8 years and 800 million euros to overcome. So how did they do it? When a man worth $100 billion decides he wants a new building for his art collection, he doesn't just buy one off the peg. Instead, in 2006, luxury brand magnate Bernard Arnault got in touch with the man described as perhaps the world's most important architect. 94-year-old Frank Gehry dreamed up Bilbao's Guggenheim Museum and the extraordinary Lou Rouveau Center in Las Vegas. This time, Gehry was inspired by the great glass palaces of the 19th century and designed a building that would set a new benchmark in extreme engineering challenges. The 11,700 square meter building was to be called the Louis Vuitton Fondation Museum. It would include a massive waterfall, 11 galleries, and a 350-seat auditorium. It would have huge steel icebergs and all be shrouded in 12 billowing glass sails. The budget was a cool 130 million euros. Frank Gehry's buildings were already notorious for challenging engineers' abilities to innovate. This building would take that reputation to the next level. James Cowie spent a decade of his life working it out.
This was not a smooth ride down the river, as we say. Myself and the engineers went to Los Angeles to meet with Gehry Partners as they proudly showed us their model of the building, what they intended to build. And they did a very, very long exposition. And they finished by saying, well, what do you think? And the structural engineer next to me thought for a second and then said, I think you used a lot of glue to make your model stand together.
Gehry's glue-happy model makers had good reason not to confront the question of how to build it. The design's sheer originality meant there was no structural template to follow. Nothing to suggest it was actually possible. But Cowie's team took a logical approach to planning the build.
It's a very tricky and complex building, geometrically, obviously, when you see it from the outside. You could break it down to 4 basic systems that put the building together.
The engineers devised a solution that was based on illusion. The huge glass sails appear to be supported by the small curving structures known as the icebergs. A signature of Frank Gehry designs, they look like the core of the building, but they're not. Melt away the icebergs and some very conventional concrete cubes emerge, within which are the gallery spaces themselves. Now these are not very Gehry, but they are very solid and allow the building's outer skin of sails to be so extreme.
They give the appearance as if these sails are floating in the air unsupported, but obviously we know that levitation of buildings hasn't been invented yet.
But to appear to levitate, the flimsy glass sails would still need many more smaller fixings, because of course, being sails, strong wind was a big concern. The forces of gravity and wind on a building would normally be calculated by computer models. But so much was unknown about these ultra-complex structures that computer modeling wasn't trusted. Getting the plan right meant going back to basics.
We built a mini building, which was not more than 50 square meters on the ground. We have all of the systems, the sails, the glass enclosure, the icebergs, and we did a test run in which we evacuated many of the problems that we would have been confronted with if we had built without doing this test.
The successful dry run gave the builders the green light. By 2011, the project had been underway for over 5 years. But as the foundations and central concrete structures began to appear, protests about the size of the building and its impact on the park intensified.
A group of Paris residents challenged, they didn't like it. They challenged the original construction permit.
A court order found the building contravened Parisian planning laws. The huge project was stopped in its tracks.
When we were asked to suspend construction, we were quite in the middle of things. And so we had to keep working for another 2 or 3 months just to stabilize the building so work could be suspended because it was in a bit of a precarious state.
With 1/3 of all the scaffolding in France on site, Gehry, Arnault, and the hundreds of specialists involved found their dream in the hands of the courts. But Bernard Arnault fought back. The court battle ended 4 months later, when the city of Paris suddenly changed its laws on land usage. Frank Gehry was back in business. While the foundations and concrete cubes were taking shape, the components that would create the steel icebergs and glass sails were being made off-site, a long way from Paris. Gehry's mixed use of material was typical and challenging. Arcing beams of wood and steel support impossibly complex glass panels, many exposed to the elements. Making these to the highest standards meant using only the very best workshops and craftsmen. Engineer Bernard Vaudeville helped coordinate the massive Europe-wide project.
All the elements are prefabricated. They are made in workshops, which are 100 kilometers away from Paris. For the glass, it's made in Italy, and the wood was made in Germany, and some other elements were made in Belgium. So all these elements had to come from far away, and they were all prefabricated.
More than 400 specialist fabricators in 4 different countries would create the 23,000 unique pieces that must somehow all fit together perfectly when assembled on site.
That's basically the jigsaw puzzle from hell.
So how did they make sure it would all slot together? The designers used a system created for a different, but even more demanding industry.
The designers used technology pioneered by the aviation industry. It's called BIM, Building Information Model. It lets all of the manufacturers add information to a 3D model and then lets the designers check what everyone is doing.
This shared virtual building model meant teams on-site and off-site were all fully aware of any problems arising and could rapidly agree solutions, dodging time-consuming meetings and expensive mistakes.
Basically, this model was the base on which everything was created, and it allowed for the contractors in different parts of the world to fabricate pieces of amazing geometrical complexity.
First of the prefabricated structures to be assembled on site were the icebergs.
We're here in the iceberg, the highest one. These shells were prefabricated in Belgium and were transported to the site, to Paris, on trucks, trailers, and assembled, as you can see, with bolts, simply bolts, with joints that you can see here. All of these shells were different. There were 365 different shells for all the icebergs of the project. It was assembled on site to compose the external shell of the iceberg.
Now the iceberg shells needed to be clad with a huge number of custom-made white tiles, which all had to be just the right size before they arrived.
Normally, it doesn't matter if you have to adjust things on site. I mean, that's part of the building process. But you can't really do that if everything is so custom-made.
Instead, Bernard's team relied on components being made to within a few millimeters of specification, so they weren't too close or far apart once assembled.
Assembling them on site is very difficult because there is something we call tolerances. Tolerances means that when you fabricate something, it's never exact, never. You can't do that. Exactitude is only divine. It doesn't exist.
On top of all this complexity, because every tile is different, each one had to be attached in precisely the right order.
You have 19,000 of these white panels. Almost all are different.
So they came in boxes. When you open the box, the panels had to be in the right order. You can't open 50 boxes in order to find where the good panel is.
With the icebergs complete, next came the huge sails. With 13,000 square meters of curving glass, these were perhaps the most challenging features of all to create.
3,500 panels of glass, with each one with an individual design, for which special ovens had to be created to manage the curve, to manage the way the surface would be treated to reflect or not reflect light.
Commercial car windscreen making combined with meticulous hand craftsmanship to ensure each panel curved precisely the right way and was safe to install.
There were multiple constraints just on the glass that required us to work with glass manufacturers to invent a whole new way of fabricating glass.
Finally, in 2014, 8 years after it began, and with nearly 800 million euros spent, the Louis Vuitton Fondation Museum was ready to hold its first exhibition. But for many, the art inside was a sideshow. Because Frank Gehry, his architects, engineers, and craftsmen had achieved something extraordinary.
The thing that I really love about this building is that the structure is on display. So many buildings, the structure, the actual bits that hold up the weight in the floors, it's just not visible. It's behind walls, it's behind cladding, you never see it. But with this structure, you can really see the columns, the frame, the skin. And to me, that's really inspiring.
Beautiful, but the work that went into it was extraordinary.
Against what had once seemed impossible odds, Paris had a new icon on its skyline, to match perhaps even that famous Tower of Steel itself.